In this video, we're going to take a look at an introduction to linear systems of ODEs. A linear system of ODEs is basically a set of equations where instead of trying to solve for one function that we've been either calling x of t or y of x, we're now trying to solve for a whole bunch of different solutions to a whole bunch of different equations simultaneously. So a linear first-order system can take the following form. So a linear first-order, and that's all we're going to look at are first-order systems. First-order system can be written in the following way. So it's going to look messy. Don't worry, they're not going to be this bad in practice. So we'll have some function x1 that we're trying to solve for. So we'll have x1 prime, and it's going to be some function potentially of t, where we've got a11t times x1 plus a12 of t times some x2 plus plus a1. And so let me just write this whole thing out, and then we'll come back and kind of readdress what this thing looks like in a minute. So that might be our first equation. So notice it's an equation where we're trying to solve for x1. We have the derivative of x1 right here, and x1 itself shows up right here. So if I just had these two terms, this would look like a normal first-order differential equation that we've been trying to solve in the past. Similarly, if I included this plus f1 term, which I should make clear can also be a function of t. If I had this term, and this term, we would know how to solve that, again, based on the methods from when we were dealing with single first-order differential equations. But it's these other terms in here that complicate things. It turns out that our x1 function that we're trying to solve for doesn't only depend on x1, it also depends on x2 and x3 and x4 and so on all the way up to xn, where those are all functions that we're trying to solve for. And we have to have a bunch of equations for each of them. So we'll have a second equation, x2 prime. And x2 prime can depend on x1. It can depend on x2, and it can depend on all the ones in between up to xn, plus some sort of non-homogeneous term over here. And then we're going to have a series of these. If we've got n different functions that we're trying to solve for, eventually we're trying to solve for x1, x2, all the way up to xn, we're going to need n total equations to solve for those. So we'll have one for all the way down to xn prime. And it will look like this. With another non-homogeneous term. So all of these, imagine the dots kind of going down to make this list. And the point is, we have n total equations. Each of those equations involves all n functions that we're trying to solve for, x1, x2, all the way up to xn. And they're all interrelated, connected together, or what we call coupled together by these coefficients, these ones that are the a's with all the different subscripts. The subscripts that we're using are just basically meant to indicate kind of basically which variable it belongs to. So in this first equation for x1, notice that all of the a's start with the number 1. And then the second number tells you which variable it's associated with in its dependency. So we're trying to solve for x1 prime, so all of these start with 1. Here's how it depends on the x1 term, so the second term 1 here matches the term here. This term tells us how it depends on x2, so notice the 2 matches the second term in our a here, and then all the way down to xn depends on, again, the nth term of our a's here. And so these subscripts basically tell you not only which variable we're solving for, that's what the first subscript tells you, but it also tells you which variable that solution is depending on for each given term. So in this case, the second number, the second one that shows up right here tells us that this is associated with x1, this is associated with x2, this is associated with xn. And that pattern continues through all of these, and we have now a big, messy system of differential equations. in general, the way that we're going to solve these is using matrix algebra. So if we were to rewrite this using matrices, we can enormously kind of compact the way that we're going to look at things. We would write this as the following. So I would write it simply x vector prime. So we'll talk about vector notation. You've seen it if you've taken Calc 3, but you may not have seen it otherwise. It's typically covered in most trig classes as well as sort of a side topic. But basically this x vector is going to be the vector that contains all these x's. So we'll define it in just a minute. So we have this x vector prime is equal to a times the x vector plus some f vector. So we can write this whole thing compactly in this form as long as we define all of these terms carefully. So where for us, what we're calling this x prime term, it's a vector that looks like x1 prime, x2 prime, dot, 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 all the way down to xn prime. Or alternatively, you may see it written as all the x's on the inside, so x1, x2, dot, 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 down to xn, and maybe put the prime on the outside, indicating that this prime is kind of distributed through to all of the different terms in this matrix. And one other thing just to point out that you may see, oftentimes we'll use subscripts and call all these terms x's, but some other textbooks may also use things where instead of calling them all x's, we might call them x, y, dot, 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 down to like some z. This is typically, again, if you're stuck in three-dimensional space, two-dimensional space, you'd use xy, three-dimensional space, you'd maybe use xyz, but spaces beyond that, if the dimension of the space goes higher and we have more than three terms or components in our vector, we typically go to this notation where we just start using subscripts to tell us all of these. So all of these notations are different ways of writing this. In the context of the one we've written, I think this first one or second one is most appropriate. It goes along with what we've got written here. So just know that you may also see x, y, and z. I think I use x, y, z in some of the homework solutions that I wrote up. So that's what x prime looks like. A is a matrix, and it contains all the coefficients. I'm calling it capital A because we typically use capital letters to denote matrices. But I'm using A because it goes with all these coefficients up here. And it's made up of all those coefficients. So we'd have A11, and remember these coefficients can potentially be functions of time. So A12, dot, 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 up to A1n, A21, A22, A2n, down to AN1, AN2, ANN. And the dot, dot, dots are meant to assume that you'll fill in the blanks from there. This x vector, we've basically already written it. This is it here without the, if we took away the prime, so it's meant to represent that same vector. So the x vector is just meant to look like x1, x2, all the way down to xn. And then lastly, the f vector is meant to be all those non-homogeneous parts. So the f1, the f2, and so on down to the fn. All of those so-called forcing terms, if you want to think about them like that, that show up over here. So basically, this is how things are set up. We are going to restrict ourselves exclusively to 2x2 matrices just because it's a lot easier, and I have to teach you a lot less matrix algebra if we're dealing with 2x2 matrices. It gets more complicated with 3x3 and above, and you'd have to learn a bit of linear algebra. So I'm not assuming everybody knows that. I think most people probably, in fact, don't know that. So I just want to give sort of a little side note on matrix algebra. How does this work? If you haven't seen this, what's going on here? So how can I write this big ugly set of equations compactly in this form under these assumptions? How does this A times this x vector, for example, how does that even work? What does that mean? So I just want to talk about basically matrix addition or matrix and or vector addition, and matrix multiplication. So really what we're going to need are those two operations. We're going to need vector addition, and then we're going to also need matrix multiplication, specifically matrix vector multiplication. So let me just do a quick sort of side lesson on how these two things work. So I think both of them are straightforward enough that we can learn by just doing an example. Imagine I have two vectors. Maybe it's a vector we're calling x plus some other vector that we're calling y, and we want to know what the result is. If our x vector looks like this, so let's assume it's a 2 by 2 vector because that's what we're, or a 2 by 1 vector because that's what we're going to be dealing with. Let's say it's the vector 1, 2, and y is the vector 3, 4. Then in that case, what is x plus y? Well, all we need to do is basically take our two vectors and add them together. So 1, 2 plus the vector 3, 4. And we do it term-wise. So this top term here will get added to this top term here, and we will get a result that is a vector of the exact same size. So these are little, what we often call column vectors because they're arranged in the form of a column. That's how we're going to deal with our vectors in this class. They'll all be in column form. You typically denote the dimensions of it using the number of rows and then the number of columns. So rows, comma, columns. So I would say that this one is a 2 by 1. So this is a 2 by 1 vector because it has 2 rows but only 1 column. And so we go in that order. And so the result of adding a 2 by 1 vector plus another 2 by 1 vector is a 2 by 1 vector. And again, to get the top entry here, I just need to add the two top entries there. So 1 plus 3. In fact, let me make it extra foolproof here. We're going to have 1 plus 3 as the top entry and 2 plus 4 as the bottom entry. So the result of that is we'll get a 4 on top and a 6 on the bottom. So that's how you add two vectors. We can do that, again, hypothetically. That's the role that we're doing right here. For example, we're going to be adding this vector f to the result of this multiplication, which we'll address in just a minute. And you can think of it as basically getting whatever result we get from this. You just add this sort of term by term from top to bottom in the vector. So we do the exact process here, but it works with real numbers. It would also work with variables. If I just wanted to call this x1, x2, and y1, y2, then the result would be for the top x1 plus y1, and the bottom would be x2 plus y2. So alternatively, if we wanted to do it with symbols, that would work as well. For matrix vector multiplication, so I want to take A times X and see what that spits out. So for us, let's say that A is a matrix made up of the following numbers. Let's just say it's 1, 2, 3, 4. So here's our matrix A, and let's say that X is equal to the vector, whatever, let's say 5, 6, just so there's no repetition of numbers, so it'll be clear where every number is coming from. If we multiply these together, what it tells me, here we go. Sorry, screen froze up there for a minute. So if we multiply these together, A times X, it would look like this. We would write it out as the 1, 2, 3, 4 times the 5, 6. We'd write them right up next to each other like that. And the idea is when we do this multiplication, we're going to go from left to right in whatever, in this case in the matrix, whatever's to the left, and we're going to go top to bottom. So basically I'm going to go this way here, and I'm going to go this way here. And what we're going to do is essentially take a dot product of this vector and this vector. And the result in this case, we would say that this is a 2 by 2 matrix. This other one is a 2 by 1 vector. And when you multiply them together, these two numbers have to match. And the result is these two numbers. This is what our result will give us. So our result will be a 2 by 1. We'll get something that is has 2 rows but only 1 column. And so the way that we would do this one, for example, is basically I'm going to take the 1, 2 vector and I'm going to dot product that with the 5, 6 vector. And if you're unfamiliar with the dot product, or if it's been a while, all we're doing is basically taking the first entry here, multiplying by the first entry here, taking the second entry here, multiplying by the second entry here, and notice again I'm going left to right in this one, top to bottom in this one. We multiply them term by term, and then we add up the results. So this result would be 1 times 5 plus 2 times 6. So I do this one times this one plus this one times this one. For the second entry, and we'll simplify that one in a minute, so we'll condense this down and actually write that number out in a minute. For the bottom term, we're going to do the same thing, but we're going to use the bottom one here. So I'm going to go across here, top to bottom here. So the first entry here, again, is the 3. This one's going to be the 3. It'll hit the, so the first term here is the 3 in this row vector down here, in this row. And it'll hit the 5, which is the first entry in the vector that we're multiplying against. So we'll do 3 times 5 plus 4 times 6. So again, the first entries here hit the first entry here, the second entries hit the second entry, and we add piece by piece. So this one on top, we're going to have 1 times 5, which is 5, plus 2 times 6, which is 12. So we've got 5 plus 12. The top value is going to be 17. On the bottom, we'll have 3 times 5, which is 15, plus 4 times 6, which is 24. So 24 plus 15, what is that, 39? And so there's the result that you would get from doing this matrix multiplication. And again, it can be done generically as well. So like generically, if I took that same matrix A, so 1, 2, 3, 4, and now I said, let's let x be just the vector x1, x2. So it does have some variables. What would we get in this case when we did A times x? Well, now that would be 1, 2, 3, 4. There's our matrix times the vector x1, x2. And again, I'm going to go across on the left, top to bottom here. So it'd be 1 times x1 plus 2 times x2. So I'd get x1 plus 2x2. That's the top entry. And then what will I get for the bottom entry? I'll get 3x1 plus 4x2. And so you'll get some practice just rewriting things like this. Basically being able to convert back and forth between these two ideas is going to be one of the important things that you need to get comfortable with first. So this is what the matrix algebra looks like. Again, vector addition and matrix vector multiplication. This is how it works. Once you know that, then basically things are going to get a lot easier. In general, our goal is going to be to take this system, and our goal is going to be to, solve for the vector x. Right? We want to solve for x. X is basically the list of all the unknown x1, x2, up to xn, all those unknown functions that we're interested in. So that's going to be our goal. This is what that notation means when you see ax. This is what's going on there. We're multiplying a matrix times a vector, and this is the type of the result that you get. So the result of multiplying my 2 by 2 matrix times my 2 by 1 vector results in a 2 by 1 vector. And hence, coming back up here, here's my, imagine this is a 2 by 2 times a 2 by 1. This is going to give me a 2 by 1. And I will be adding it to another 2 by 1, right? That is going to be the goal. The f's are basically just a vector, and the result of all this other mess, the a times x, it's going to just give us basically a big vector where the first term is this big long mess, the second term is this big long mess, and so on. So we'll see how that works again via example in just a minute. Let me touch a little bit on the theory, but we covered a lot of the theory that we're going to need way back in section 4.1 when we were introducing kind of the theory behind higher order differential equations. So the theory of all of how this works. So the theory for solving these systems is very similar to the theory that we already covered of solving nth order linear ODEs. So the stuff that we did back in, again, chapter 4. What I mean by this is a couple of the things that we talked about then are going to come back up. So that idea that we had about superposition, you'll recall we talked about superposition. I'm not going to go into a ton of detail. I'm just going to give you the definition. It should look pretty familiar. So if we basically let a bunch of solutions show up, so we've got x1 vector plus some, not plus, let's write this as a list, x1 vector, x2 vector, and so on and so forth up to xk. And these are all solutions. So they are a set of solutions to, let's say, the homogeneous version, x prime equals ax, because this is going to be what we're going to focus on first. We'll always focus on the homogeneous one. So what makes this homogeneous? The fact that there's no plus f term. This is the generic form of a homogeneous system. So just keep in mind, this is going to be homogeneous because there's no plus f vector term. If there was a plus f vector, that would be the non-homogeneous part of this thing. Okay, so this is our homogeneous equation. What it says is if all of these individually, if all these vectors can be found and they all solve this thing, then any linear combination of these will also be a solution. And that's how we're going to construct our more general solution. So our general solution would be x equals c1 times x1 plus c2 times x2 plus dot 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 plus up to ck times xk. Right? So if you have individual things that solve it, then any sum of those things, sum of any combination of those things is also going to be a solution. So then this is also a solution. So this was the idea behind superposition. We're now just applying it to these vectors. The other one had to do with what we called linear independence. We talked about this back then. This is going to come up again. So linear independence. So same thing. Let's let this list x1, x2 up to xk. So again, for me, when I write vectors, it's just going to be a normal lowercase letter with what I'm attempting to draw as like a little arrow on top. Try to clean that up, make that look a little nicer. So I usually write my arrows like this, just kind of like a half arrow. But that is the notation I'll use. I should mention in the book, if you're reading the textbook, oftentimes instead of using these arrows to indicate vectors, they'll just bold the letter. So if you see a letter that's been bolded, that typically indicates a vector. It's just I cannot handwrite a bold letter and make it distinguishable from my non-bolded one. So that's why I'm doing these little arrows. So let me just mention that here, and maybe I'll put a little side note in a second, write that down so you have it written somewhere as well. But for now, these are, again, our set of solutions to x prime equals ax. Turns out if the only solution, so the same idea as before, if the only solution to the following, to c1 x1 plus c2 x2 plus dot 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 all the way up to ck xk. If the only solution to that being equal to 0, but now because these are all vectors, we're adding up a bunch of vectors, the result should be a vector. So we'll write this as the 0 vector, and note that the 0 vector is literally just a vector of the same dimensions as these ones, but every entry in that vector is zeros. We'll call it the 0 vector. If the only solution to this equation is that all the c's are equal to 0, then the x's are linearly independent. So this is, again, the mathematical definition. Essentially, what it's saying is you can't find a way to write one of these terms as a linear combination of the others. There's no way to take this vector and two of these vectors and wind up with this vector, because if there was, we'd be able to find a way. I'd just take this vector plus two of these and then subtract off one of these, and we'd be able to get the 0. But what that means, the fallout of all of this, is essentially that for us, when we're dealing with 2 by 2 vectors, it's very simple because 2 by 2 is going to be what we're looking at. So if we simplify this down to only having 2, the only way to ensure that this one and this one, there's not a way to make them add up to 0, is to make sure that the two vectors themselves aren't proportional to one another. You can't get this one by just multiplying this other one by a constant. And that's going to be the result when in the case of dealing with a 2 by 2 system, which is what we'll be looking at. One vector should not just be a straight multiple of the other vector, or they are not going to be linearly independent. They point in the same direction in that case and are not linearly independent. In practice, this is not what we're going to do. In practice, we'll use the same thing we did to decide if our results were linearly independent before. We computed a Wronskian. We have another Wronskian to compute here. We can check. So in practice, we check by computing the Wronskian. And for us, our Wronskian, which we'll use that same notation W, of x1 and x2 all the way up to x sub k. The idea is that we basically smush those vectors together into a big matrix, and then we take the determinant of that matrix. So we're going to have the determinant of, imagine this is our x1 vector, and it goes up and down. We'll write it there. Then we'll write the x2 vector next to that, up and down here, then so on and so forth, all the way up to the kth vector as a column vector. These arrows are just meant to say, here's how I'm arranging the terms of the x. So if x1 is equal to the vector 2, 0, and x2 is equal to the vector, whatever, 1, 3, when I'd smush them together like this, the Wronskian of those two things is going to be the determinant of, we do 2, 0, again, arranged vertically. That's what those arrows are meant to indicate. And then 1, 3 right next to that. So that's how we would do it. So we just smush them together, and if we get 0, then they are not linearly independent. If it's not 0, then they are linearly independent. So if the Wronskian, which is computed by smushing them together and computing this big determinant, which for us, it's just going to be a 2 by 2. Every example we'll do is a 2 by 2. So again, this times this minus this times this. In this case, we would get 6 minus 0, which is 6. It's not equal to 0. So these are linearly independent. x1 and x2 are linearly independent. And we could also just see that by observation. This vector is not just a straight multiple of this vector. Whereas alternatively, if I said, here's my x1 and my x2 is, I don't know, 3, 0 instead. 3, 0 and 2, 0 would not be linearly independent because I could just take the 2, 0, multiply by 3 halves, and I would have 3, 0. So again, not equal to 0 implies linearly independent. So linear independence. If it is equal to 0, then they are not linearly independent. Okay, there we go. So hopefully that sounds familiar, nothing too scary or too new. What's next? So we talked about superposition, we talked about linear independence. Let me just define our fundamental set again. We had that term show up, our fundamental set of solutions. So what are we looking for when we're trying to find a solution? It turns out in this case that any set of n linearly independent solutions, so linearly independent solutions, meaning x1, x2, all the way up to, in this case, xn, that solve the original differential equation that we're trying to solve, which is going to look like x prime equals ax, where a is what we're going to call an n by n matrix. So again, this is the dimensions. It's telling us n rows, n columns. So it's basically made up of n separate equations, each with n total variables in it, if you want to think about it like that. So that is what we got. So any set of n linearly independent solutions where n is the basically n by n is the size of the matrix that we're dealing with anyways, that makes our fundamental set. So you can think of it kind of as we did before. We've got n equations. We're going to need basically n solutions, as long as those n solutions are linearly independent of one another. So back when we solved for second order differential equations, we always needed to find two linearly independent solutions. In the case of what we're dealing with here, again, we're going to be solving almost exclusively 2 by 2 systems of equations. So A will always be 2 by 2. And again, that means that we will only need two linearly independent solutions to form our fundamental set of solutions. So is a fundamental set. Let me complete this sentence. There we go. A fundamental set. I will also just mention, what do we do if there's a non-homogeneous equation? Notice all the equations that we've talked about so far take this form, x prime equals ax. That's the ones we talked about, kind of how to, the superposition, all that good stuff. Well, what happens if it's non-homogeneous equations that we're dealing with? So, well, it turns out the general solution to these will be put together in the exact same way that we did for like second order equations. So the general solution to, imagine it's x prime equals ax, there's the homogeneous version, but now it's non-homogeneous because we add some additional term plus f. And again, this f could be a function of whatever the independent variable is, so presumably t in this case. But this is what makes it non-homogeneous, the fact that we have this plus f term. The general solution to that is x equals what I'll write as x homogeneous plus x particular. The x homogeneous term will be formed by taking any linear combination of these things that form our fundamental set of solutions. So this is going to be like c1 x1 plus c2 x2. And then the particular solution can be found basically in the same manner that we've done in the past. So we're going to have method of undetermined coefficients and variation of parameters. They'll just take a slightly different form because we're dealing with systems now instead. So just to be totally clear, where xh, which typically will look like c1 x1 plus c2 x2, is the solution, is the homogeneous solution. I.e., it solves x prime equals ax without the plus f term. and where x particular, the particular solution, is the particular solution which can typically be found using either the method of undetermined coefficients or variation of parameters. And these formulas will look slightly different than what we were doing when we were dealing with like a second order equation, because now they're going to be involve matrices and vectors instead. So just real quickly, the only thing that I need you to take away is that basically we're going to be constructing our solutions in a familiar way. Stuff is going to look very similar to what we did when we were doing higher order differential equations with just a few new wrinkles. The thing I want you to get comfortable with, though, is how we rewrite equations. So how do we for now, let's focus on that. So let's say, here we go, rewriting equations, or systems, I should say, not equations, systems in matrix form, and back and forth, right? Being able to convert back and forth between sort of our system form and our matrix form. So as an example, let's say that you were given the differential equation, the system of differential equations that looked like this. They said dx dt is equal to 4x minus 7y plus whatever, let's say minus e to the t. And a second equation, dy dt, is equal to 5x plus 3y plus 2e to the t. So this is a system of equations, right? It's two equations, and how many unknowns are there? Well, we're trying to solve for x, we're trying to solve for y, and they both show up in each equation. Both x and y are clearly functions of t, and we have these other non-homogeneous terms that show up here. So basically, you can think of this as being kind of our, what we were calling our x vector. It's the derivative, so it's x vector prime, right? Here's dx dt over dy dt. These terms here can be thought of as the result of doing a times x, and then the last term here we can think of as our f vector. And so we can rewrite this, and we can go either direction by doing the following. I'm going to think of this as basically, we could write like d dt of the vector xy. And that would be equivalent to what I've got written right here, dx dt on top, dy dt on bottom. So I have x on top and y on bottom, but we're applying d dt to the whole thing. So we'll have dx dt on top and dy dt on the bottom. You could think of them like that. Alternatively, you could have just written dx dt on the top and dy dt on the bottom. This is interchangeable, right? Those two things are equivalent. So I like this because it's just a little bit more compact than having to write out this. So you can pick and choose what you prefer. But again, notice in this case, I'm not writing this as x1 and x2. I'm just calling them x and y. Okay, so what it's going to be equal to? I know it's going to be equal to some a times x. So here's my x vector again. My x vector is just x and y. So this is basically this part right here. This needs to be our a. So here's our a, here's our x vector. And again, this vector over here, if I wrote it out on this side, this is basically our x prime vector. So what does a need to be, remembering how we do our matrix vector multiplication, to give these coefficients? Well, I know for my top equation, I need to have 4 x's and negative 7 y's. So if I were to go across and try to get the top entry as the result of this, I need 4 x's and negative 7 y's. So I need a 4 to hit the x and a negative 7 to hit the y. And I can do that in the following way, 4, negative 7. Now this would hit this, right? The first hits the first, the second hits the second, and we add the results together, right? So 4x, negative 7y, and we're adding those results together, and that's our top entry. How do we get the bottom entry? Well, the bottom entry should correspond to the bottom equation. I need 5x's and I need 3y's, and so it's simply 5 and a 3. And once you actually do this a couple of times, again, remember we're going this way here when we do our multiplications. If you're comfortable with matrix vector multiplication, this gets to be pretty straightforward, but even if you're not, it's pretty easy to compare these two and see that the position of these numbers correspond exactly to the position of where these numbers showed up over here, right? As long as I write my x's before my y's, right? 4, negative 7, 5, 3, 4, negative 7, 5, 3, in the same pattern. So there's that, plus now we need our f term. We'll just put them in a matrix. I'm going to have negative e to the t for the top entry, and then 2e to the t as the bottom entry, and this plays the role of my f vector. So you can rewrite this equation, where it's written as two separate equations out rather, so this system, which is written as two separate equations, can be written as a single matrix equation, and that's what we've done over here. So you need to be able to convert back and forth between these, and you'll get some practice early on in the homework. So I don't want to do a ton more. There's more examples in the book if you want to look at that, but I think this is pretty straightforward. So for now, theory-wise, just to summarize, make sure that you understand the stuff that we were doing back when we were doing chapter 4 and 5, the stuff with higher order differential equations. The same ideas that applied to all of those are going to apply to our systems of equations. We will stick to 2x2 systems, and we will also stick almost exclusively, certainly in the homework, I'm going to only give you homogeneous equations. I'm not going to give you any that involve the non-homogeneous part where you have to find the particular solution. Not because it's not necessarily useful, but just because we've kind of already done that and we're running out of time in the class, and I'd rather move on to other interesting topics. So if you could figure out what the particular solutions were for higher order differential equations, you'd be able to apply the formulas in the same way to figure out the particular solutions to these systems of equations. So for now, this is it. In the next video, we'll talk about how we actually solve systems of equations like this.